Welcome to another open learning session where I'm going to catch up with deep learning. Last time we have done the compact representation of systems of linear equation, and today we reached 2.3, chapter 2.3, solving systems of linear equation. Okay, so let's just go in. So in 2.3 we introduced the general form of an equation system. That's what we already know, where the elements are basically numbers, and the b's, the values here on the right side, they are also numbers, and they are known as constants. Okay, that's good. So a constant is basically a number we know. They don't change. And x are unknowns. And then we have different x axes. X goes from 1 to m. X goes from 1 to n, and I goes from 1 to m. So I is basically the first one, which tells us how many equations we have, and the size of the vector, or the length of this vector x, tells us how long the equation is. Because basically they have to fit, right? If you write in a matrix like this and you have a vector x, this length has to fit here. That's how you know that the length of the vector is basically the length of the equation. Okay, so the next one is here, the next sentence. Thus far, we saw the matrices can be used as a compact way of formulating systems of linear equations, so that we can write AX equals B. Moreover, we defined basic matrix operations such as addition and multiplication of matrices. In the following, we will focus on solving systems of linear equations and provide an algorithm for finding the inverse of a matrix. So we will focus on solving, and we will provide algorithm for finding the inverse. And we have to remember, not every matrix has an inverse, but the shape, I think, is not important here. If we go back, here the inverse. Yeah, when a matrix inverse exists, it is unique. Okay, in this case, the matrix is always a square matrix. But could you have an inverse of a non-square matrix? So if your matrix is 3 times 2, so it has such a shape, you could think of a matrix which has such a shape, 3 times 2, no, other way around, 2 times 3, and if you multiply them together, you will get a rectangular matrix, 3 times 3. We know that the identity matrix has to be a square. Okay, I don't see a reason why the inverse, why only in square matrices have to be, what I mean is, I don't see a reason why non-square matrices cannot have an inverse, but I guess we will find this. Okay, let's go back. Yeah, so the next chapter is 2.3.1, particular and general solution. Before discussing how to generally solve systems of linear equation, let us have a look at an example considering the system of equations. We have a 2 times 4 matrix and a vector of 4. And then, of course, we will have a 2 times 1, or basically a vector. The system has 2 equations and 4 unknowns. Therefore, in general, we would expect infinitely many solutions. This system of equations is in a particularly easy form where the first two columns consist of 1 and a 0. So that's what they say. The first two columns, they're only ones and zeros. Remember that we can find scalars x1 to x4 such that the sum of all x's times c equals b. So basically, this here is the equation where we can find ci to be the ith column of the matrix and b the right side at the right hand side. A solution to the problem in 2.38 can be found immediately by taking 42 times the first column and 8 times the second column. Okay, let's try to understand this. So what's important is this part. And here we have b, which is 42, 8. It's a vector. And then they say it's enough just to take x1 and x2. So what they're saying is we only have two equations here, and we only need two variables, and everything else can be 0. So they just put a 0 in x3 and x4. So actually what you would expect is to have here plus x3, and then you would have 8, 2, then plus x4, and then minus 4, 12. But because they are just saying, well, we can just ignore those, they are 0, because we put a 0 in the x's, we can just focus on the first part. And this one is really easy because you have basically like something like a base. You have a 1 on one side and then a 0 on the other side. So you can just put the number here as well, because you know that you need to have 42 for x1, and then you can just say, yeah, x1 is 42, because let me try to explain it better. So you have b1. b1 is green, and this is b1, and this is b1. And then you have b2, which is red. This is b2, and this is b2. We have x1 and x2 here. Now we want to have how much of those x1 and x2 goes into b1, the green one. And we know that because here we have 0, that x2 has no impact on b1. Therefore, only x1 impacts. And how big should x1 be to be like 42? Yeah, it has to be 42 itself. And the same is true for x2. Yeah, that makes sense. Okay, so this is what they call a particular solution. So in the whole solution, you cannot forget x3 and x4, which is 0. And they are writing it here as a transposed version. So a transposed version of a vector is basically left to right. We have to remember that a vector is just like a matrix. Here you have a 4 times 1 matrix. This is our vector. 42, 8, 0, 0. And when you transpose it, this is basically the line where you mirror it. Like if you transpose it, then your vector becomes something like this. So 42, 8, 0, 0. And that means that this one is 1 times 4 matrix. So our solution is exactly that in yellow. And they say the solution is called a particular solution, or a special solution. So two words for the same thing. It means that there are more solutions, it's just like one of many. However, this is not the only solution of the system of linear equations. To capture all of the other solutions, we need to be creative in getting zero in a non-trivial way using the columns of the matrix. Adding zero to our special solution does not change does not change our special solution. What? Adding zero to our special solution does not change the special solution. Not really sure what they mean. I think they mean with adding zeros, these zeros. To do so, we express a third column using the first two columns, which are of this very simple form. Okay, so what they do is they take our particular solution, and I think they try to use a trick. Okay, let's try to understand what they're doing. I'm going just to mark the numbers. Maybe we can see a pattern here. They try to express the third column using the first two. So this is the third one. This is the first, this is the third one. And then they say, okay, let's use the first one here and the second one here. And yeah, so they have to be 8 and 2. Otherwise it would not be the same. And then they put a 0 on one side so that 0 equals 8c plus 2c minus 1c plus 0c. What is c again? C is the column. Okay, so 8 times the first column plus 2 times the second column minus 1 times the third column plus 0 times the fourth column equals 0. They cancel each other out. Then you have the solution here. Yes, and if you have 0, you can scale them with any scalar. Does not change. So the scalar is somehow an infinite set of basically versions of the same vector. Following the same line of reasoning, we can express the fourth column of the matrix using the first two columns to generate another set of non-trivial versions of 0. So here we have used the third one on the left side, and then I think we just do the same thing with the fourth one. So they say, okay, this one here, let's take a look. It has to be something like C4 equals minus 4C1 plus 12C2 plus 0 times C3. Yes. So what do we have here? Minus 4 plus and minus C4, because C4 goes over there, then becomes minus. Okay, so they do the same thing here, and then they say, yeah, we also have a scalar, lambda 1, and then for the second equation, lambda 2. Now let's understand how they put this together. They say putting everything together, we obtain all solutions of the equation system in which is called the general solution as the set. Okay, this is a set. Okay, so we have our first solution. We just put the solution back in here. This is our first solution, yellow. Then we have our second solution, I think this one, and our third one is here. So our third one is here, our second one is here, and the first solution is here. So because the first solution is the particular one, there's no lambda. Okay, so why do we have a lambda here and not there? The reason is that this equals to an actual vector, where here we are equaling 0. So what do they say? They say the general solution is not one vector, but a set, like like different vectors. They put all the vectors in a set, and they say this set is 4-dimensional. That's what they do here. It's 4-dimensional, and this set has to satisfy this equation. It has to satisfy this equation yellow plus blue plus red. And yellow and blue and red, they have a scalar, and this scalar can be any scalar. Okay, so this whole thing happened because we had 2 equations and 4 unknowns. So we have more questions than we have answers, which means that the answer itself cannot be fully answered. Like we cannot know all the answers. And what we can do is we can constrain it by putting it into a new, like formulating it into a new equation. And then we still have these 2 variables somehow leaking. But at least it's not like the set of all possible x, like 4-dimensional vectors. It's all the 4-dimensional vectors which are constrained by this equation, which is like a lot less, I would say. Like this is like at least some intuition. Like you have to understand, okay, here on top we have the number of equations are how many answers we have, and the number of variables or unknowns are how many questions we have. And if we have more questions than answers, then something is missing, so you cannot solve the whole thing. Which means that you might find a particular solution, like one point or so, one vector, where it makes sense, but you will not find all the solutions. So this is what you can already understand by just looking at the equation. And then you can figure out, okay, 2 things are missing. So in my general solution, there must be like some kind of a linear equation with some like 2 variables. Okay, so let's continue. Remark: the general approach we followed consisted of the following 3 steps. First, find a particular solution. Find all solutions to where the matrix times x equals 0. Combine the solutions from step 1 and 2 to the general solution. Yeah, so it's important that we understand that, like, if you would just take a look at the equation, you can find the particular solution. It's quite easy, I would say. But how do you know how the blue and the red equation is formulated? And the trick is to look at the columns. I still remember that you can think of these columns as dimensions. So each one of those like are, I'm not really sure, but they are like dimensions and they belong together. Because we found a solution for the first 2 here, this dimension is missing, and it has to be always a column, no matter how many rows you have. In this case, it's a 2 times 1 column, but it could also be like a I don't know, 100 times 1 column. And then you will have as many equations here as you have columns left. That makes sense. Neither the general nor the particular solution is unique. The system of linear equations in the preceding example was easy to solve because of the matrix, has this particular convenient form, which allowed us to find the particular and the general solution by inspection. However, general equation systems are not of this simple form. Fortunately, there exists a constructive algorithmic way to transform any system of linear equations into this particular simple form: the Gaussian elimination. Key to Gaussian elimination are elementary transformations of systems of linear equations, which transform the equation system into a simple form. Then we can apply the 3 steps of the simple form that we just discussed in the context of the example. So basically they're saying it's not always easy, but there's a system where we can transform it into this simple form, and then we can just use this approach we just had. This is it for this video. See you next time.